Hello, my name is Andrew Kopp, and I'm here with Luke Miller, David Demery, and Grant Wong. We're here presenting our control system's automated chicken coop door system. We started off the project by conducting some interviews of some local farmers in the area. The first was Ben Gaitis, and one system that we were considering before conducting these interviews was an automated chicken coop door opener. And when we talked to Ben, it was very solidifying that this was actually a need because he had previously purchased an automated chicken coop door and he really liked it. He said it was well worth his money. So this told us that it was a product that was actually useful in the market. The second person that we interviewed was Catherine and her husband, Tim Moreland, and they had a manual system in their chicken coop. So they were just using a string to manually open the door in the morning and close it in the evening. And they were really excited about having the system automated so they didn't have to go out there every morning and evening. Some of the needs that we identified was we wanted the system to open the door at or around sunrise and close the door at or around sunset. So it would do automatically. We also wanted to have a manual ability for Catherine and Tim to change the state of the door if they needed to, aside from the automated system. We also wanted the system to be reliable, for it to last multiple years, problem-free, so that they wouldn't have to touch it. They could just set it and forget it. Looking at the market, there are currently several automatic chicken coop designs available on the market. Many of the designs do not offer easy user flexibility for changing when the door opens and closes. This is something that, as you'll see, ours addresses very well. Additionally, our design will fit most vertical-oriented doors and is not specific to a single door design, unlike some of the other devices on the market.
Here's a list of our inputs and outputs we had for the system. The most significant design constraint we had was with the motor. And so we actually went over to the Morelands with a force gauge and we measured how much force it takes to open the door. From there, we were able to calculate torque, and then we were able to purchase the necessary motor. So here's the user interface that we have for the Morelands. Starting from left to right, you have the button, which is a manual override. It works in both the auto mode and the manual mode, which is what Andrew explained prior. Then we have a toggle switch. This changes between the manual and auto mode. And again, the manual mode is there, so you don't just plug it in, it just starts working. And so the auto mode uses 3 LDRs and they're all averaged. And they're embedded on the outside surface of the barn, so they're always exposed to ambient light. The LDRs take a data point every 2 minutes, and it takes 2 consecutive data points in order to change the state of a door. And that's just in case a cloud comes around and makes it dark for just like a few minutes so it doesn't open prematurely. And then the potentiometer, it changes the threshold for when it opens and closes, depending if they want it to open or close when it's lighter or darker. And then the LDR error light uses a percent difference equation. And it basically just compares all 3 of the LDRs and it throws out an LDR that is significantly different. And in doing so, it'll blink when 1 or 2 of them are broken, and it'll hold red when all 3 are broken. Then on the mechanical side, we have the spool and the motor, and the spool just winds up the rope to open the door. When the door opens, the motor turns on, and it'll hit the wooden dowel will hit the first limit switch, which you can see in the bottom right. It'll hit the first limit switch, the motor will turn off, and then the wooden dowel will sit in the mechanical latch, which David will explain later, and that'll hold it open. And then when the door closes, the door is lifted up out of the latch, it'll hit the second limit switch, motor turns off, and then it'll move past the latch, and gravity will bring it to a close.
So here's our electrical drawing. We use this to actually solder the system together so we know how everything would fit together. And then on the next slide, you can see we've got our mechanical drawings. So on the left there is the mechanical drawing for the total latch assembly. And on the right is a SolidWorks rendering of our box, which houses all of the electronic components. So we had a few initial design problems with the latch design. This design relies on the center of mass being behind the lever so that the lever hangs with the slot underneath the dowel on the door so that as the dowel drops down, it'll go into the slot. Unfortunately, the center of mass was too close to the lever and it was not hanging in the correct position. So we overcame this by drilling holes in the lever to lighten it, and then we added a bolt on the back of it to shift the center of mass to the left on that diagram. So you can kind of see the difference between before and after on those two pictures there. And this solution actually worked pretty well. It worked perfectly after we implemented it. Then we had some problems with the wiring. Troubleshooting it posed quite a challenge. This isn't actually our system in the picture, but it kind of felt like it was this much of a mess at certain times.
Yeah, so getting into the cost a little bit, it cost about $96 for all the components that we ended up incorporating into our system. And the biggest contributors to the cost were the motor and the power transformer. We believe this design will be successful because it's simple. It's really just a LDR that's reading the light sensor, or that's reading the light, I should say, and sending it back to the Arduino. That light reading is being compared to a set point, and based off of that comparison, it'll open or close the door. So it's really easy. It's a really simple system. It's universal for any vertically actuated chicken coop door. It's practical and it's inexpensive. So that $96 cost is about half of what the other automated chicken coop doors that are out on the market currently kind of cost. So we're thinking that we would be able to have a cost advantage if we were to take this into market, just because of the relatively inexpensive nature of our components. Finally, we'd like to, in the future, we'd like to make the wires cleaner, just to make it easier to install. We'd like to have higher quality light sensing equipment. So the LDRs that we are using are relatively cheap for this prototype model. We'd like to get light sensing equipment that's a little more consistent in its readings. And then finally, it's always a good thing to reduce costs when it comes to developing your product. So that would be our third goal for future improvements. So with that, thank you for listening to our presentation.